Hello, welcome back to C567. Um, Today we work on a new topic, which is the Earth pressure. For this lecture, we focus on a few learning objectives. First, we will introduce you about the backfill of our retaining wall, and we also learn how to draw stress distributions behind the retaining wall. And also, the next thing is that we revisit a concept that we learned. Um, we talk about the different Earth pressure conditions at rest, active, and passive. So we revisit the concept that we learned in CE 467 in your undergrad geotech design class. Lastly, we will introduce you how to come up with the parameters of Ka and Kp, those active and passive earth pressure coefficients through the Coulomb and Rankine theories. So earth pressure distributions. So here you have got retaining wall behind a backfill, could be a sandy material or other like earth material. And we look at the at-rest conditions, which is the most simple one. So assume wall. So you got a wall here. Assume this wall is at rest. So this wall is retaining or is supporting the backfill behind it. And the backfill, the soils, it has a unit weight. So it kind of sustain the horizontal stress. If you look at soil elements, then you will sustain a horizontal stress that you can calculate, which is equals to, well, first of all, vertical stress. This should be this supposed to be something we have been knowing by heart now. How to calculate the vertical stress is the unit weight of soils times the depth Z here, or the elevations Z here, and you got the salt elements. So at different depth or locations of the behind the wall, then you will find the horizontal stress. No, sorry, first the vertical stress, and the horizontal stress is a functions of the vertical stress, and for the at-rest conditions, you will have the K naught parameters. So this is the K here is stand for the earth pressure coefficients, and this is K naught is the at rest, because at rest means the wall here is not moving. We will talk about active and passive conditions, and those is corresponding to how the way that the wall move, whether into or out of the soil. But anyways, here is at rest conditions, so the wall is not moving. So this K naught is at rest earth pressure coefficients, and the horizontal stress will be equals to, or the coefficients of the K naught will be equals to the horizontal stress divided by the vertical stress. The horizontal effective stress divided by vertical effective stress. And be very careful. This K naught or any K values that we talk about, K or Kp, all of them must be effective stress based. Again, this is very important. So those earth pressure coefficients, it must be at uh, effective stress base. It says totally not equals to the total stress base, or any K values that uh, calculate or final form a total stress space is absolutely wrong. It must be effective stress space. Okay, so you got the stress here now, and when we look at the stress distributions, assume that we have a homogeneous soils, which means all the inner rates is the same, and throughout the whole uh, layers or the whole stratums of the backfill, everything is the same in terms of unit rate. Then the stress distributions behind this wall is kind of like a strict line. So at the bottom of your wall, right here, so at the bottom of the wall here, so here will be kind of like a strict line again for the distribution of the stress. And this part be equals to K naught times the unit rate. So pretty much this is the horizontal stress. So throughout like a different depth, you have the horizontal stress, but in terms of the z instead of the h, because at the bottom of the wall, then you have the whole uh, thickness or the whole height of the wall. So here is equals to h at the bottom of the wall, which means it's sustain try to provide all the loading. And the locations for this force adding on the wall will be at this like a center of this triangle. So you got like a triangular stress distributions there. So this is kind of like a stress distributions. And this the center of the force will be adding at 1/3. So it's the center of the triangle. Uh, that's the locations of the force that adding on. So we can call this the P naught. This is the resultant force for the backfill adding on the wall. Okay, now what if the case that we have a water table, we have partially saturated, or we have the bottom part of the wall being saturated, which is very common for our retaining structure. And this water tables can goes up and down because it depends on the rain seasons and also other water recharge that you may happens to your retaining wall. Um, so when you have water, things got a little bit more complicated. Well, first, the top part of it, when uh, above the water table, you still have the dry part. So it will be just like the same thing we look at before. So in terms of the stress distributions, so again, this will be kind of like this z-axis, and here could be the pressure. So if we look at those axes there, um, so this part will be K naught times the unit weight of the soils. So when this is dry, we have the gamma, and we saturate it. So it's effective stress base or the effective unit weight. So it's gamma pine. But like at the top part is still dry. So at the bottom of on the right at the water tables, right above the water tables, the horizontal stress will be equals to K naught times the unit weight times H1. So let's say here from above the water table here, is H1 right there. So that is the distributed stress above the water tables, and underneath the water table called this to be H2. And you realize that like after for the part that the soils is submerged in the water, the unit weight will decrease because in effective stress base, the effective unit weight will be equals to the total unit weight minus the uh, unit weight of water. So if you are like in the British units, so this will be about, I make this up, this could be about 120 pound per cubic feet. So common value for sand, for kind of like medium dense sands, and unit weight of water is 62.4 pound per cubic feet. So the weight now is kind of like about being half. Uh, so the pressure, the increase of the pressure, you would expect will be smaller, but like underneath the water table, right? Uh, you still need to sustain at least the same amount of the stress, and then until you're hitting the bottom of the wall. Oops. So this is the bottom of your wall. And then now you have the effective stress base that will be go up maybe with a smaller slope. That belongs to the submerged water. Um, and this part here will be equals to K naught. So here will be equals to K naught times gamma H1. So the bottom part, sorry, the top part plus the bottom part. Now you have effective unit weight times H2. So that is the pressure that is it is adding on. Um, and you will have two part of resultant force, right? So again, this will be happen at the 1/3 of your top part, and then here you for this another area, this will be at 2/3. Sorry, another 1/3 of uh, the center of the triangle. So when we do examples, we will talk more about how to locate this uh, overall resultant force. We need to take the moment, but we talk about how to find out uh, examples. So that's pretty much like the stress distributions for the soil, and then like don't forget we still have the water part. So the unit weight of the water will be increased linearly since encountering the water table. So here will be the distributions of your water. This is the distribution of the water. So this is the water pressure. And at the bottom here will be the unit weight of water times H2. And the overall pressure will be equals to the summations of the two. So which means you will have first of all you will have the dry part, that we talk about. And then you also have the soil plus the water part. Adding on it. So pretty much like again, this part will be equals to K naught unit weight times H1 again. And here at the bottom part will be equals to the K naught times the gamma H1 plus gamma pi H2, and also plus the unit weight of water times H2. And here maybe now is a better times to in fact look at the resultants, the locations of the resultant for us. You have different shape of area, and you need to find out the locations or the center of those area, and then take a moment, and then we will find the resultants of the location, the resultant for the sum for the overall project, and or the overall like a retaining wall for designs. And we will talk about that like we more in examples. Your example here. So we are designing here a retaining wall that try to retain the soil behind. The wall is 4.5 meter tall. We are designed for the arrest conditions. Um, and at the depth of 3 meters, that's where the groundwater tables locate. Um, so this is a sandy materials, and given that the sand has OCR of 1.5. Uh, and since sand is a sand material, so you don't have any cohesions, but you have a friction angle of 35 degrees, and the unit weight of the soil above and below the groundwater tables also given. So since we are designed for the K naught conditions, so first of all, let's calculate the K naught values. So the K naught values will be equals to 1 minus sine 3 points OCR sine 3 point. So those equations we discussed it like C366 and also C467. So when we talk about soil mechanics is undergrad classes. We talk about how to find out the K naught for both for the soil, both at normally consolidated state and also overly consolidated state. And if we plug in this formula for 35 degree and also OCR of 1.5, we got the K naught values equals to 0.538. And now if we calculate the stress at the depth of 3 meters here, so the horizontal stress, effective stress, will be equals to K naught times the unit weight times the depth. So here is 0.538 times the unit weight is equal to 15.7, and the depth is 3 meters. So if I plug in all the numbers, then we will get 25.34 kilonewtons per meters uh, square. So stress. Um, at that point, since there's no water yet, so that's why the effective stress will be equals to total stress. And if we have at the bottom of the retaining wall at a depth of 4.5 meters, So the vertical stress at this point will be equals to 3 times 15.7 plus 1.5. Now this you need to consider the effective stress since this part, the bottom part of the soils is submerged in water. So this the unit weight minus the unit weight of the water in SI unit, which is 9.81, and this is equals to 61.19 kilonewtons per meter square. And the horizontal stress against everything need to be on an effective stress base, and then that will be equals to the K naught times the vertical stress, and the K naught is again the same thing, 0.538. Um, and the effective horizontal stress at the bottom will be 39.92 kilonewtons per meter square. And if we just calculate the water pressure, it will be equals to 1.5 times 9.81. That will be equals to 14.72 kilonewton per meter square. Then we can plot out the stress distributions. Um, so you will be first we have the 3 meters, and also we have the wait, let me do it here. So for the stress distributions, we will have the here this part up to this point is 23.53. That's 25.34, and we will be adding the additional stress that we get from the submerged like soils, and this part is the stress that we calculated, 39.92. So here is the horizontal stress we are working with, and this is in terms of kilonewtons per meter square. So that is our stress distributions, and you break down into 3 parts. So this is our first or 3 areas, because eventually we want to know the areas uh, to calculate the locations for the resultant force. So this is my second area. And the third area for the stress distribution plot right here. And also don't forget about our water pressure. So our water pressure is start from here. So the water pressure will be equals to, at this point, that we calculate 14.72. That is our water pressure. And you also have another area of force that you we need to consider, which is from the water pressure. And let's use blue for the water. So the stress distributions is very powerful because with the stress distributions, it help us to find out the lateral force, P naught, because eventually we want to find out the amount of the lateral force adding on the wall and also the locations of this lateral force. And the lateral force will be equals to the area that we just calculate or we just find out for the stress distributions. So the lateral force will be equals to uh, so let's call this to be area 1, this is area 2, this is area 3, and this is area 4. This will be equals to area 1 plus area 2 plus area 3 plus area 4. So now it's just algebra. Try to find out the area. So the first one is a triangle. So 1/2 the base times the height. And then plus the second area would be a rectangle. Would be equals 1/2 times 25.34. And then now we have another triangles, which is 1/2. So this part here will be equals to 14.58. The difference between 39.92 and 25.34. So that will be equals to 14.58 times 1/2, and then finally the area of the water pressure. So 1/2, 1/2 times 14.72. So this is the water. This is the bottom part of the soil pressure, effective stress base, and this is the total stress base, and this is the bottom part, the top part of the soil, the dry soil. If we calculate all this, the area. So the resultant force is equals to 98 kilopascal, just kilo newtons per meter for this case. So this is the force per meters. So this is kind of like the unit length into and out of the page. So this is not stress. It's a force, force per unit length. And then like we would first we answer the questions, the magnitudes of the lateral force. Next is we try to find the locations of this lateral force. Then what we need to do is taking moment at point C. So this is our point C. If we summations our total moment at point C, um, which is the bottom of the wall. So and the locations, because C bar here would be the moment at point C divided by the loading, the lateral load that we just find out. So so pretty much like is the force time the locations equals to the sum of the moment at the bottom of the retaining wall. So if we do this, so assume this is the piece of knot. So this will be the location we try to find. So we try to take all the force, or like put it the other way better, just like the apples. So this is the force provided by the wall to the soils. So this is the moment that we try to find, and v equals to like the moment that so this moment, this force of times the moment arm here upon C will be resisting all the moment uh, provided by each of the loading there, the loading from the soils, including the water. So now, as we try to equate the two different driving and resistant moments, um, so this, oops, would be equals to 38 times O1, which is the area that we talk about for the so the area for the our first area, and the locations for this loading force from the area will be this moment arm here. So we have 1.5 and then plus 1/3 because it's a triangle. So this shape. So like the resulting force for this area must be at the 1/3 of the area. So it'll be 1.5 plus 3 divided by 3. So this is 1.5 plus 3 divided by 3. So this is kind of like the locate the center of the triangle, and this is 1.5 because the triangle is 1.5 meters above the bottom part of the retaining wall. And then likewise, the second area again the force is 38.01, and then this is a rectangle. So the center is located at half of the height. Maybe 1.5 divided by 2, and then the third area again is a triangle. Now this time is located at the bottoms, and the area we calculate already is 10.94, and this is 1/3 from the bottoms, and same as the water. So this is the water pressure at the end, area number 4. This is 1.5 divided by 3. And divided by the resisted by the total moment, so which is like 90. I mean the total resultant force, which is 98 um, of them, and then we calculate the moment arm for this resulting force will be equals to 1.76 meter. So with that, we know this locations here is 1.76 for this resultant force provided by the retaining wall to resist the soil behind the wall for at-rest conditions. Okay, so what about beyond the at-rest conditions? We went into the cases of active and also passive earth pressure. So what does it mean? What does it mean by active and passive earth pressure? It all depends on the displacements of your retaining wall, whether it is into or out of the soil body. So when there's like a no movement at all, we call arrest conditions. So for example, for this graph here, if we um, identify the movement of the wall as delta L here, if delta L is equal to 0, then we will be at the arrest conditions, this right here. So here is when we are right at the y-axis. So y-axis is the K at this times, which is the earth pressure. Um, so the earth pressure for arrest conditions. So if this is right at no displacement, so this is the arrest conditions. If that is the case, means the wall is not moving. But like for the case that for the wall is moving away from the solid body, so like this graph here, uh, we call it active conditions. Since the wall is moving away from the location from the soil, so the K here will no longer be K naught. We call it Ka. Since you can expect the horizontal stress for the soil element here will be feeling very different than everything is not moving or at rest. You could expect the horizontal stress in that scenario will be less, right? Because the gap between the soils or the soils is allowed to mobilize, so the horizontal confinements of the stress is less. The other case is what we call a passive conditions. So this case is like your wall is your design, your wall is pushing into the soil. So it depends on your design scenario. You need to make an engineering judgments there. What kind of scenario, what kind of displacement or performance of the wall you're expecting. If you're expecting the wall will move away from the soil, then you need to design for the Ka conditions, the active conditions, or you are on a project that the wall you will be experience another loading, from other kind of like construction activities or other loading that is support from other buildings that you will push the retaining wall into the soil. Then you need to find the KP. You need to design for the passive conditions. Now this time, the wall that is going into the soils. And you kind of like actually it's kind of like a rotations. If we define the wall as the height is h, then like the movement that you have divided by h, it gives you the rotations. But at the end of the day, again, is all it matters is like whether you are away or into, or you're not moving at rest conditions uh, for this k parameters. And for the case that for arrest conditions, the k naught values is about zero point 0.5. It's not exactly zero point 0.5, but just going to give you some ballpark numbers. It's about zero point 0.5. Uh, and we talk about this. So K naught is equals to 1 minus psi phi pi. This is for normally consolidated soils. And for overly consolidated soil is equals to this formula here. 1 minus psi phi pi times OCR to power sine phi pi. So this is how to find out the K naught. So K naught is more established or more straightforward, but for Ka and Kb will be very uh, complicated because you involve soil structure or the retaining walls and backfill soil interactions. Uh, but the overall trend, as you could expect, uh, the more away, right? The more pretty much like if you're in active conditions, when you are the more away from the soil, which means the gap between your wall of the soil, or you are mobilizing more and more soil, backfill soils, then you expect the lateral confinement, the lateral stress, right? Because you allow um, your system able to relax such that the displacements or the rotations become larger and larger, and the Ka value will become smaller and smaller. And but you need to expect that if you have too much displacement or too much like a movement, then you expect failure to you may occur. And This Ka values would flat out between zero point 0.2 to zero point 0.4. Um, so this part is the Ka, and the other part is the Kp. And again, for the passive conditions, the furthermore you push into the soil, you expect a higher stress. So that's why the Kp value can go as high as 10, because like uh, this Kp here dictate the amount of horizontal stress. As you can imagine, it's like when the wall like going further and further into the backfill soil body, and then the resistance provided by the soils will be higher and higher until you fail the soil. You load like too much, and then failure occur. Same as the Ka conditions. You go further and further away until to a point too much soils mobilize at the backfill, and then the whole retaining wall system will collapse. So now it's a concern, or it's a matter to how to find out this Ka and this Kp. And we will introduce two different theories. One is from Coulomb, and one is from Rankine. Okay, so let's start with the Coulomb theory. So there's a couple assumptions associated with the framework that Coulomb has established many years ago. Is I believe is from 1700s. Um, but anyways, like first, based on his framework, is assume when the soil fell behind the retaining wall. So, for example, you see here you see a retaining wall right there that is trying to support the backfill soil behind, and he has first of all he assumed this is a plane strain problems, which means like this is like a two. You can imagine this as a imaginary plane that make this become a 2D problems. Means like for the soil behavior that I mean like the system behavior that like into and out of the page, uh, if we dimensions like coming out or going to the page is infinitely long. So the whole thing works as like 2D cuts on a piece of paper. And the soils that you're working on, you will have a friction angle of V pi and also cohesions of C pi. And you assume like a perfect drinkage, which means the soil has no water, and it is more likely work better for cohesionless soils because you need to assume there's no water means like you have very good drinkage. And if you're clay, then you hold up the water. But sand materials for backfill, this Coulomb method will work well. And you assume it is you have a failure wedge. So the whole thing will react like a rigid block. With the failure happens at triangle ABD. So this is the failure wedge. So here should be ABD. So this one, triangle ABD, is the failure wedge. So the whole thing will fail as a block goes together. This is one of the assumptions. And the failure surface and the ground surface are planes. So yes, so here is your failure surface. And the ground will also go as a plane. Those are the assumptions. And the friction coefficients between the wall and between the soils wedge is tangent phi. So here you assume you have a friction angle right there. So when this wedge fell is slide against the concrete wall. So it depends on the material of your retaining wall. You can adjust the this delta parameters right there. So, but there's frictions. It does assume the frictions exist between the soil and the wall. And a couple more terminology is alpha is the slope of the retaining wall with the height h. So you have the height h right there for the retaining wall, and we have slope angle alpha. Um, so you take care of different dimensions of the retaining wall. If you have very simple kind of like right angle wall, then in that case, so this is your backfill of the soils. In this case, the alpha equal 90 degree. And beta is the slope of the backfill. So if you have a level fill, then beta equals 0 for level backfill. So that is the setup for the Coulomb theories. Um, and what he did many years ago, a couple of hundred years ago, is try to solve for the resultant force felt by the retaining wall. So eventually, a bunch of trigonometry problems is try to solve for this PA, which is the resulting force provided by the retaining wall to resist the soil movement. And this can be done in both active or like passive conditions. So how do you do it? First, he assigned the angles. Rho here. So rho is the failure wedge orientations, and this angle here depends on your failure wedge. So each time, like for us to solve this problem, we need to define this failure wedge orientations, or like we need to find a way to search for the orientations that give you the most likely failure conditions. Uh, Anyways, we will get there. But that defines the failure wedge, which is the triangle A, B, and D right there. So first of all, is to calculate the weight of the saw wedge. W per length. Again, this is a plane string problems. It's a 2D problems. So the other dimensions go out of the page. We assume that is a unit. So it's kind of like per 1 meters, per meters, or per feet. When we deal with this problem, so we become like the pound per meter or pound per feet throughout the problems when solving for the force. So before finding the weight of the soil wedge, we need to find the area. So the area of triangle ABD will be equals to 1/2 times BD times AC, as you have seen from this figure. And within the triangles, the ratios of the one side to the opposite angle. So BD divided by sine. So there's a sine law right there. So BD divided by sine alpha plus beta equals to angle. Sorry, the sine of AD divided by sine alpha minus beta. So there's a trigonometry work right there to represent the angles within the triangles, and then we organize it. So now the size of BD will be in terms of alpha and beta, and also the unknown rho right there. And for the in triangle ADC, then another right angle triangles take care of the sine, and then like we can express AC in terms of AD for angles of alpha and also the rho. And for side AD, again, it is right angle triangles, then is equals to H over sine alpha. So if we plug all this back to the area calculations, so 1/2 times BD, we find out BD already, and also we know AC. Then we get this area formula. So this is area equals to that part. And, and then like the weight of triangle ABD will be equals to the unit weight times the area. Again, this is a plane string problem, so everything can be expressed in kilonewtons of force per uh, unit distance. So when you have the unit weight pound per cubic feet times the area, then we have like the pound per feet. We assume unit distance unit into and out of the page. So if we have the unit weight times the area, so we know the area from the previous equations, and we assume this is a homogeneous solid backfill. So the come with a standardized unit weight right there, gamma. So this is expressions of the weight of the failure wedge in terms of the other known parameters like the unit weight, the height of the wall, and also the some angle orientations. Alpha again means the slope angles of your retaining wall, and beta is the slope angle of your backfill. So we know there's a couple like forces right there to resist to make the whole thing to stay equilibriums. We know um, the weight, so the weight of the saw wedge, and also we know the resultant force on when the soils slide again of on each other along the failure plane for the wedge, saw wedge, and also the supporting force piece of A. So and you will come with a slope angle. So you will come with a slope angle. So for the resultant force provided by the retaining wall to sustain the soil behind it, and this part yeah come with an orientations, and it has this horizontal and also vertical component. We talk about that later. But anyways, like for this three forces that we just mentioned about under equilibrium, you should form a closed loop. And we know the orientations for the force. For example, the weight of the wedge must be pointing down because it's that weight that is a weight that attracted by the gravity. And we know the reaction force or the resistant force along the soil wedge. So this is kind of like both the force that from the soils uh, supporting the or like holding up the failure wedge from soil to soil. And also, do you this is at the end of the day, this is what we try to solve for, the piece of A. The resultant force or the reaction force provided by the gravity wall to sustain the soil body. So you give us a similar triangle now. because of the force that's forming a closed loop. So using the sign formulas again, we want to find out the P sub A, the resultant force provided by the active conditions, derived by the sign, which is the angle opposite, the opposite to it, and then equals to the rate of the whole thing that we just calculate for the failure wedge, and then divided by this angle right there. Pretty much 100 degrees, subtract the other nose angles. And after we reorganize the formula, then we can express our P sub A, the resultant active force in terms of the geometrical parameters that we can measure and also we can design for, which is now we have those unit weight of soils, the height of the wall, and also the angle orientations, alpha, which is the slope of the retaining wall, and beta, which is the slope of your backfill. Uh, and now, what being controllable, what being in terms of analysis, is the angle rho. So this angle here represents the orientations of the failure wedge. So it really this angle which really depends on the nature of the soils where so we can explain in the systems, such that like it will be the wedge that you fell uh, uh, when the retaining wall no longer able to sustain the loading behind it. So mathematically, we want to solve for, and now you can see that this value here, while the other parameters that we mentioned about, those kind of like physical parameters, like the height of the wall, or like the unit weight of the soils, the slope of the backfill, those are physical parameters that you can change, right? Or is your the size of the wall is your constructions, however tall, like however whatever slope that you need to work for a project. So those are physical parameters, and the only parameter here now is being like a mathematically uh, or like more related to the soil behavior is the angle wall here. So you can see the piece of A is a functions of the orientations of the failure wedge, and we need to find the one that the one that indeed is the provide the smaller support of the from the retaining wall. So mathematically, we can do a search, and the search of this angle, the slope of the failing soil wedge, can be found by differentiations. If we differentiate our piece of A, which is the resultant force from the wall, with respect to the angle that we just talked about, we should give us like a minimum active force to mobilize the wall. So if this d force divided by the angles is equal to 0, then we should able to identify mathematically. We should able to identify the uh, the minimum active force. So after we do the differentiations of this lengthy formulas right here, and then put that equal to 0, then we can solve for the P sub A. So this is the P sub A. Through differentiate the equations that we talk about, and then like we solve for it, then that represents the minimum active force to mobilize the retaining wall. So that will be meaning the values of the retaining wall that can sustain. And after that, like we compare with the stress distribute diagram. Because this is the force that we mathematically through the Coulomb theory that we can find out, and through the stress distributions we know the force is equals to 1/2 the earth pressure, now is the active conditions, times the gamma and h square. So it's exactly like the very first part that we talk about which is this stress distributed area. So uh, the force that able to sustain this area, which is the force, then active conditions, then that means is the capacity of the water we want to find out. So after we have the P sub 8, when we compare with this formula, and then we can find out the K sub A, the active earth pressure, which is equal to this equations, that represent the K sub A that we want to look for, we want to solve for. K naught, like, relatively easy, but like K sub A, uh, the deviations from Coulombs many years ago is lead to this point. This is the generalized like solutions for finding K sub A. If we have a little bit more, first of all, like, we talk about this too. This P sub A here is acting on our wall, retaining wall with an angle. And if we just want to find out the horizontal part of it, then we do trigonometry, like times the cosine angles. It happens that like you have a 90-degree right there, so is equivalent to 1/2 k naught ka sine alpha minus delta times gamma h squared. So we get this by comparing these two formulas. So that's why the h squared, now we have the square terms. And similarly, like for the k terms, ka terms, if we want to find out the k, what is equivalence to based on the Coulomb theories, uh, then like we take care of the angles right there. So uh, we multiply by the sine alpha minus like a delta. So this is our k generalized forms, which means you also have the uh, backfill slope with the angles of beta, and also like other terms right there. Then this is our Ka active earth pressure at the horizontal directions. If we further simplify it, for example, we have a level backfill, uh, and we assume the interactions angles. Uh, the delta is equal to 0. So which means like this part, like, 0 means like a horizontal force. And in that case, if we assume like, this horizontal force, and also like there's a level backfill, which means no stopping ground behind the wall, then this is the K sub A through the Coulomb method. So the K naught is understandable, but now this is the K sub A, the active stress. And similarly, if we work through the trigonometry for passive conditions, realize that when you have passive conditions, the orientations of the resultant force from the wall will be different, because now you're pushing the soils into the soil. So you can expect, like, when you valve the wedge, you slide this way, versus the other one when the ball is moving away from it, then like you have uh, from the surface, the soil wedge sliding downward. So that's why the orientations of the reaction force from the soils, and also provided by uh, the the retaining wall, those forces you will see you will be at opposite directions. Now, if we do go through a similar mathematic exercise, then we should able to solve for the case of P, the passive Coulomb theoreticals earth pressure. So the case of P, and then like for the case that you have a level backfill, we will and also is a right angles retaining wall. So this for in order to for those like K simplified form of KA and KP, uh, we are at conditions that we have a right angles, a retaining wall, a level ground. So this is alpha equal 90 degree, and this is also the beta equal to 0. And we assume there's like no friction between the solid and the wall. Friction less over there, then we will have a simplified formutation. Okay, next, we talk about the Rankine theory. So this one now, this time, this the Rankine theory is more like focused on the stress state rather than kind of like a block or wedge failure that like you assume a rigid body or solid mass that goes down. So this ranking method pretty much like is solved from a piece of solid elements. So you can see here on this figure, based on the stress state of a solid elements that are behind the wall, and then like a solve for it to find the Ka and Kp, the coefficients. So the main difference, another main difference between this Rankine and Coulomb method is this uh, Rankine method. It has a p defined failure surface, which is 45 degree plus 3 pi over 2, versus, so remember when we talk about a Coulomb, the failure of the Coulomb method is uh, you need to search for it by through the differentiations. You find the minimum resultant force provided from the retaining wall. So, you know, which the same problems, but like I mean, like the same site, but like you have two different engineers or scientists back to the time. So the Coulomb versus Rankine, both are very famous scientists at that time. Coulomb was in the 1700s, and Rankine is about a little bit more than 100 years after him. Uh, in 1800s, he come up with another approach to look at the essentially the same problem and try to figure out the stress or the horizontal force that a retaining wall can sustain. But anyways, like this is his approach. He used a stress state method, which means like he focused rather than like a global failure wedge. He look at like solid elements uh, behind the wall and solve from a stress state. And but like he has some limitations that now like he need to predefine the failure surface with an angle failure surface angle right there, 45 degree plus phi divided by 2. So again, like it has a bunch of assumptions. First, you assume the problem again is a plane string problems, which means again, into or out of the page, like you assume like a unit over there. So it helps you to simplify the 3D problems into 2D problems. Um, and then like you also you favor the cohesiveness of soils. So particular this ranking method, you only have assume the soil has a friction angles but no cohesions, and it also assume there's no water at all. So it's a well drainage, a well drained sand materials. Um, and the soil mass is a state of a plastic failure. So it is at a particular stress state, at the failure state. If you understand the Mohr circle, you understand what does it mean by we need to focus on the at the state of failure, because when you draw more circles, you can represent. Remember, like you try to represent most UU tests, right? When you work in the lab, you working on either UU tests, the unconsolidated undrained tests, or unconfined compression tests. Uh, you can see like how sigma 1, while like sigma 3 is fixed. but sigma 1 just keep changing until it hit a failure. So which means like sigma 1 is keep increasing. So when you draw more circles, you can have the radius and diameters keep increasing, increasing, increasing to a point that you fail. So if you draw more circles, it's evolving more circles, and now they just look at the point of the failure. So at sigma 1 equals failure. Um, well, like the Coulomb method, the Rankine method, the failure surface and also the ground surface planes. We talked about that in the previous Coulomb method. And another major difference between Rankine and Coulomb is now they assume there's no frictions between the soils and the wall. Previously, you have it. Previously, when the wedge fell, uh, we assume there's frictions between the wall and also the between the wall and uh, uh, the soils, but now this time we assume there's no frictions. So despite it helping, the frictions are supposed to be helping to keep the soils stabilized behind the wall, but here they take away those advantages. So Coulomb method, Rankine method is the best to explain by the Mohr circles because it is a stress state method. So that's why the Mohr circles explain this work perfectly well. So before everything start, right? Before like you mobilizing the soil in active conditions. So this is your horizontal stress. Pretty much this is your sigma 3, and this is your sigma 1. And then like you keep mobilizing the soils because we know that the active stress, remember we talked about this. So you have your when everything's at rest, the K naught is something around like a 0.5, could be 0.6 or could be zero point 0.4. Depends on the OCR. Right there, we talk about that. So is a factor that's less than 1 for the K naught. And for active conditions, you must like less than the K naught. So that's why like when we draw more circles, uh, we know sigma 1 and sigma 3 will be a portion of sigma 1. So that's why like you will get like sigma 3 always on the left hand side on the sigma 1 on a Mohr circle space, and then you draw uh, the half circles that represent your at rest like a Mohr circles. And in active conditions, your K value is even smaller than the K naught. So you would expect that uh, you have uh, Ka conditions are more close to 0. And when you draw the Mohr circles, these represent the active state of it. And in that case, the failure, you will be closer and closer to the failure line. So because this is the Mohr Coulomb failure envelope. So we talk about all this in 366. So this is the Mohr Coulomb failure envelope. So that's why from at rest conditions, your circle is growing larger and larger toward the active conditions, which means like a smaller sigma 3 until to a point that uh, so again, this is kind of like a evolving Mohr circles, right? So this is your at rest conditions, and the more and more you mobilize your retaining wall, the circle will be going bigger and bigger until to the point that now you are hitting your failure line, which is the Mohr Coulomb failure envelope. At that point, it is your failure stress state. So that is what we designed for. And this is our soil properties. So the size of your active failure Mohr circles will depends on uh, the friction angle, which is how strong is your soil, is your sand right there. So until you're hitting that. So if we look at this established like more circles, we look at the triangle ABD right there, and then you know the angles that play with it. So this is angle phi right there, and you do the sine of that, and then you work on the geometry, um, and then like we can represent the horizontal stress in terms of the vertical stress. Um, Again, this is the sine, uh, a theory of sine right there. So sine angle phi point equals like a BD over this. So this is a right angle right there. So BD over two part of it, AO, and also plus OD. Um, so, and the D is the center of the failure state of the Morse circles. So you know that this part right here, AO, right there, this part is this terms, and this part pretty much is the OD. So the radius of your Morse circles right there. So you're having those terms. And then like we can express our sigma pi AH with this formula right there, or like you work on the math or work on the geometry. Then this part will be we define this to be our Ka values. While this again the square root of Ka. So this should be the square root of Ka right there. So this gives us the formula, and with that we can find our Ka values. And when we start these problems, this is just the we assume that the backfield has level ground, so there's like no stopping to start these problems. But this is like through the Morse circles, we can find the Ka values and all this stuff on the state of the stress. And then, similarly, this is the passive conditions from the Rankine method. So this is your initial stress state. So this is the vertical stress, and this is the horizontal stress. And um, the circles right there essentially is the same thing here. The scale is different, so that's why one may look larger and the other one may look smaller than it looks like. But those are the initial state, the arrest condition. They're the same thing. But think about it, like now you have passive conditions, which means you're pushing the soils or the wall into the soils. So you expect the K values will be greater than 1. Because at passive conditions, the horizontal confinement will be larger than the vertical stress because now you are forcing the soils to push against each other, and then you will cause a very large lateral stress. So that's why when we plot out this diagram, now our horizontal stress will be much larger than my initial vertical stress. So at the failure state, so when we keep pushing the soil, right? Again, it's evolving more circles. So when we keep pushing the more circles into the wall, you will get larger and larger until we hit the failure stress state, because now you're touching your uh, molecular failure envelope again, and that like a failure envelope is bounded by the soil properties, the friction angles. So with that, that also like the Rankine ways to explain how to form the failure state. And with this theoretical framework, Rankine, he look at on the small circles, he look at triangle uh, ABP again, and he take the so this phi sine phi over there. So he take sine phi equals to this side divided by the hypothesis size, which is here, which include the AO plus OD. Oh, sorry. So the triangle he look at is ABD again. So it's not this one to start with. Because the triangle is ABD to start with this one. So very similarly, he looked at around the sine law with the known solid parameter to substitute in, and then he worked out the geometry. Then he come to this phase, uh, and find out Kp will be equals this term. So this is Kp. It's supposed to square root. So Kp will be equals to the terms over there. So Rankine also, use similar method. Now you have a little bit more complicated geometry because now you have a backfill with an angle beta right there, both active and passive conditions, and also work out the Moore circles because now they look at the stress state and solve for more genetic form now for K and Kp. Because now you also have not only the friction angles, but also have another geometry of the slope of the backfill to solve for Ka and Kp. So those are the Rankine equations for finding the lateral earth pressure. Okay, let's try an example. So here we have retaining wall again, supporting level backfill, sand material, and we are designed for active conditions. So first, we want to find out the Ka values for each of the sand layers, and the other good thing is at least this is like a level backfill. So if we use the Rankine method, the Ka value will be easy enough to be find out for the two layers. So the first layers, the friction angle is 30°, which gives us a Ka value of 1/3. And for the second layers, now this time, um, the friction angle is 35°. So we will get a different answer. So after this two, then we can calculate the horizontal stress. So first, at the depth of 3 meters, we want to find out the horizontal stress at active conditions. Equals to the Ka1 times the vertical stress, so equals to 1/3 times 3 meters and then times 16 kilopascal. So equals to 16 kilopascal. And the other thing is at 3 meters, we also need to consider the lower layers. So this is the upper layers. But for the lower layers, this time we have different materials, which is the different friction angles, give us a different horizontal stress. So this time is 0.271 times 3 times 16 again. Give us a slightly different number, which is 13 kilo newtons per meter square, which is the kilopascal. And at 6 meters, The stress will be equals to, so first this is the vertical stress equals to 3 times 16, the dry sand, and then plus now we are at the bottoms of the second layers, and this is a effective stress because this is we need to consider effective feeding rate because it's submerged in the water. So this is 72.57, and this is the vertical stress and horizontal stress, and you really need to think about what are K values or Ka values you should use at the since we are looking at the 6 meter, the bottom of the second layers, so we will use the Ka2. The Ka values belongs to the bottom layers, and the Ka2 is 0.271, and then times the vertical stress that we just calculate. So this time the horizontal stress would equals to 19.06, sorry, 19.67 kilopascal. So with that, then we can plot out our first stress distributions. It's always good to have the stress distributions to help you to know what's going on, and also the stress distributions helps you to calculate the force because if once you see the area, then that equals to your force that you need to find out. So we have two layers here. First, this part will be equals to 16, belong to the first layers, and then that belongs to the first Ka, and then you also have the second Ka, which is 13. So this is how the K value feel on the stress for the first layer. So here is will be 13. And then at 6 meters, this is the stress belongs to the both the first and second layers. So here is 19 plus 167. So we finished the soil part, and then we will have the water part. Um, for the water stress, you will be equals to at the bottom of it. So the water pressure will be equals to 9.81 times 3 equals to 29.43 kilopascal. So that will be the water pressure. So this is the water pressure right here. So at this point is 29.43. And then if we combine the two parts, the soil stress distributions and the water distributions, let me do it here. Then the first layer, it didn't change much. Let me use black this time. So the first layer won't change much. So here is still 16. And then we have the 13 right here from the first layer of soils, but you have the second layers of the Ka values. And then we add on the two parts, the soil parts and also the water pressure, and give us a different slope here, which will be 36 plus 1. So which belongs to this part and this part. So here, well, If we add up those, like a 19.67 plus 29.43, that's what you got. So this is what we get for the 36.1. So we have like kind of like three areas now to work on. This will be area 1, area 2, and area 3. Kind of like a three force that we summarize. So the force will be equals to, well, is now is a matter of finding the areas. 1/2 3 times 16 plus 3 times 13 plus 1/2 times 3 times 36.1. So those are the three areas that we talk about. Then we got the three forces, 24 plus 39 plus 50.415. So the resultant force that resisted by the retaining wall under active conditions, we got 117.15 kilopascal. Sorry, not kilopascal, kilonewtons. This is a force per unit length, because this is a pain-strained 2D problems. So this is the force per meters per the dimensions that into and out of the page. So we got that one. But then now the question is, what is the locations for this force to be at? So we know this PA, then now we need to find out the locations. And again, we take the moments for this at this point. So the moment arms, and then solve for the moment arm for the resistance force. So which is equals to your first loading that you got, which is 24. And the location is 1/3 from the uh, first triangles, plus now this is the rectangles, the second part. The moment arm is half of its height. And the third triangle that you got, the blue one that you have is, again, the location is 1/3 of its height, because it's the center of the triangles, and then summarized by the total resultant force. And again, this is the three part that we mentioned. Then we solve for this, we got 1.78 meters. So which means the resulting force will be adding at the height of 1.78 meter from the bottoms, and the resultant force for this retaining wall under active conditions is 117.15 kilonewtons per meter. So last but not least, when we compare the two different methods, Coulomb and Rankine, first realized that like the two share some common assumptions or common set up by Coulomb, by the great Coulombs and the great Rankines. First, they both focus on cohesionless soils for backfills. They assume you have a homogeneous backfill materials, and the stress they are isotropic, um, and under pain strain conditions, which another fancy word of is semi-infinity, is again, which means like into and out of the page, like is consistent, so you can go for infinitely long into and out of the page. Essentially, we can like normalize it by unit dimensions. Or again, the whole materials or the whole backfields are well drained, so no build up of water pressure if you want to use those two methods. That's the assumptions. And overall, our Coulomb method will give you less earth pressure than Rankine's for level back slope. So research have been done. People use like this for the same site, use both method to assess and find the results and find out. Usually, Coulomb will underestimate the earth pressure uh, than Rankines. But like when you have a sloping ground, then you will kind of converge for the two method when the angles and the sloping angles is getting close to the friction angles between the soils and the concrete face. And another key difference again is that we mentioned this before is for the Coulomb method, it does assume or it does recognize there's frictions between the wall and also the soils. Meanwhile, for Rankine doesn't like look at it. And also another very fundamental difference is Coulomb defined um, the failure angles for every design, which means like this angle here, the size of the wedge, grow you pretty much the procedure we search for it through the um, derivative to find out the minimum uh, angles, the minimum like resultant force from the wall. But for the Rankine method, it defined it as a fixed angle at 45 plus phi pi over 2. It's a stress state analysis. In order to have the stress state analysis look at the soil elements behind the wall, you need to define the failure plane rather than coulombs like you search for it. So which one is better? Seems like the Transportation Agency in the United States, they like AASHTO's, they prefer the Rankine method. Is as written is them in their manual. But other like opinions or other agency, they may have different preference whether using coulombs or Rankine. So when we doing the my suggestion is like when you do the design for those retaining structure, very likely very popular like for geotech small business. If some of you interested in starting your own business at some point of your career, I know many like a small size company, like a one-man company, or like when people start, like many people look at focus on those retaining wall business. When you deal with that, you need to be very careful. Make sure you understand who you work for and what type of uh, standards, between you and your clients, or between you and the pipe, or sometimes it's state-owned properties that require you specific guidelines or manuals you need to follow through. Well, likely, transportations, if it's a Caltrans-owned properties, they may prefer the Rankine method. But again, like different agency, different owner, they may have different preference in terms of which way uh, to go.